Hello students, in the previous lecture we have discussed about the D block elements, their general characteristics and the general trends in their properties, that is the atomic and ionic radii, their metallic character and melting and the boiling point. So let us start with the remaining properties. So first is the density. As we move from left to right in a transition series, the atomic radii decreases due to increase in the nuclear charge. कि जैसे जैसे हम left to right पीरियड में जाते हैं ट्रांजिशन सीरीज में, जो एटॉमिक रेडियाई है वो क्या हो जाएगा, डिक्रीज होता जाएगा. क्यों? क्योंकि देयर इज अ इंक्रीज इन द न्यूक्लियर चार्ज एंड ड्यू टू दिस एटॉमिक वॉल्यूम डिक्रीजेस, बट there is an increase in the atomic mass, as we know that density is directly proportional to the atomic mass and inversely proportional to the atomic volume. So in these case the atomic volume decreases whereas the atomic mass increases, and due to this the density automatically will increase. So that's why in case of the transition element the density increases as we move from left to right in a period. But there is a one exceptional case, that is the zinc, which is having the lowest density because of large atomic volume, as zinc is having completely filled d orbital. So next is the ionization enthalpy. It is the energy which is required to remove an electron from the neutral isolated gaseous atom. And the first ionization enthalpies of d block elements lie between the s and the p block elements, कि जो उसकी वैल्यू होगी वो s और p block elements के बीच की होगी. That is, it is higher than those of the s block elements whereas lesser than those of the p block elements. And in a particular transition series, ionization energy also increases as we move from left to right, but this increase is not an appreciable one. That is, it is not a regular one. As it is clear from this picture also, no doubt there is an increase in the ionization enthalpy as we move left to right in a series. But this increase is not a regular one. There is just a small increase in the ionization enthalpy. Although the first ionization enthalpy in general increases, but the magnitude of increase in the second and third ionization enthalpies for the successive elements in general is much higher. Okay? No doubt first ionization enthalpy increase हो रही है, but the second, third and so on ionization enthalpies will always be higher in magnitude as compared to the previous one. Mostly the third ionization enthalpy is always greater than the second one, which in turn is always greater than the first ionization enthalpy. And the increase in ionization enthalpy is primarily due to increase in the nuclear charge and decrease in atomic size with increase in the atomic number, which makes the removal of outer electron difficult. क्यों? क्योंकि जब भी हम लेफ्ट टू राइट मूव करते हैं किसी भी ट्रांजिशन सीरीज में, वहां पे क्या होगा बेटा, एटॉमिक साइज क्या हो रहा है, डिक्रीज हो रहा है, बट जो न्यूक्लियर चार्ज है वो क्या हो रहा है, इंक्रीज हो रहा है. तो उसकी वजह से क्या होगा, जो अट्रैक्टिव फोर्सेस होगी बिटवीन द न्यूक्लियस एंड द इलेक्ट्रॉन्स विल बी मोर, सो इट्स वेरी डिफिकल्ट टू रिमूव एन आउटर electron from that particular atom. So that's why the ionization enthalpy will increase in a particular transition series, as the transition elements involve the gradual filling of electrons in the n-1 d orbitals. क्योंकि जैसे जैसे हम सीरीज में मूव करते जाएंगे क्या हो जाएगा, d इलेक्ट्रॉन्स का जो नंबर है वो क्या हो जाएगा, बढ़ता जाएगा. ठीक है. So this electron provides a screening effect. No doubt the screening effect of d orbital is always weaker one, but when their number increases then there is an increase in the screening effect also, and it shields the outer ns electrons from the nucleus. So due to this, the effect of increase in the nuclear charge is partly cancelled by the increase in the screening effect. So the effect of the nuclear charge on the outer ns electrons is somewhat less than the actual nuclear charge. क्यों? डी इलेक्ट्रॉन्स के बढ़ने की वजह से क्या होगा? स्क्रीनिंग इफेक्ट बढ़ जाएगा। स्क्रीनिंग इफेक्ट बढ़ रहा है तो वो ऑटोमेटिकली क्या करेगा? जो हमारा लेफ्ट टू राइट मूव करते वक्त न्यूक्लियर चार्ज इंक्रीज हो रहा था वो इस इफेक्ट को क्या करेगा? नलीफाई करेगा, उसके ऑपोजिट डायरेक्शन में वो जाएगा। तो उसकी वजह से क्या होगा? जो आउटर इलेक्ट्रॉन्स हैं एग्जैक्ट न्यूक्लियर चार्ज फील कर रहे हैं वो क्या हो जाएगा? इट इज लेस देन द actual nuclear charge, and due to this there is an increase in the ionization enthalpy along the periods of the d block element, but this increase is a very small. So it is clear from this also, this is the first ionization enthalpy, second and the third one. So as the number of the d electrons increases, so the screening effect will increase, and due to this no doubt there is an increase in the ionization enthalpy, but that increase is a smaller one, as it is clear from this. For it is in this case the value of the ionization enthalpy is almost very close to each other, and as we move from left to right the value will be remain same. So first ionization energy, the first ionization energy for the first four 3D series element, that is the scandium, titanium, vanadium and chromium are almost same. वो क्या हो जाएगी? Same होगी. Why? Because of the increase in the screening effect, that is differ only slightly from one another. Whereas the values of the first ionization energy for iron, cobalt, nickel and copper are also very close to one another. While in case of the zinc, the value of the first ionization energy is considerably high due to the extra stability of the completely filled 3d10 level, as zinc is having the completely filled d orbital. So in this case it is very difficult to remove the outer electrons. So in that case the first ionization energy is very high. Now next is the second ionization energy. The second ionization energy increases more or less regularly with increase of the atomic number. कि जैसे जैसे atomic number बढ़ता जाएगा जो second ionization energy है वो भी क्या होती जाएगी? बढ़ती जाएगी. But the value of the second ionization energy for chromium and copper are higher than those of their neighbors. Why? This is due to the fact that electronic configuration of chromium positive and copper positive ions have extra stable, that is the 3d5 exactly half filled and 3d10 that is the completely filled orbitals. So in that case it is very difficult to remove an electron from the half filled or the fully filled orbital because they are already the stable in form. Clear? So in that case the value of the second ionization energy is very high. So next is the ionization enthalpy value for the 5D series are higher than that of the 3D and the 4D series. जो 5D series है बेटा उनकी जो ionization enthalpy होगी वो हमेशा 3D और 4D के comparatively क्या होगी? ज़्यादा होगी. Why? Because in the case of the 5D series there is involvement of the 4f orbitals. As in the case of the 5D series, electrons are going to fill up in the 4f orbitals, and the shielding power of this 4f electron is very weak. So due to the weak shielding of this 4f electrons present in the 5D series transition elements, the ionization enthalpy will be very high. So next is the relation between the ionization enthalpy and stability of a metal in a given oxidation state. With the help of ionization enthalpy, we can easily predict which of the two metals in a given oxidation state is thermodynamically more stable. कि इसके behalf पे हम बता सकते हैं कि हमारे पास कोई भी दो different metals हैं same oxidation state में कि which one is more stable. For example, when a metal in the zero oxidation state is converted into the metal having two oxidation state, then energy required is equals to the sum of the two ionization energies, that is the first ionization energy and the second ionization energy. Similarly, if this metal is converted into the metal having the +4 oxidation state, then the total energy which is required to remove these 4 electrons is the sum of the 4 ionization enthalpy. That is the first ionization enthalpy, second, third and fourth one. So on the behalf of this, we can easily tell that whether out of this which one is more stable. So considering the case of the nickel and the platinum, as in the case of the nickel, the sum of the first ionization enthalpy and the second ionization enthalpy is 2490 kilojoule per mole. That is, if we want to convert the nickel to the nickel 2 positive ions, then it requires this much amount of the energy. Whereas if we want to convert the platinum to platinum 2 positive ions, then it requires this much amount of energy, that is the 2660 kilojoule per mole. And it is clear from this, the ionization of nickel to nickel 2 positive requires lesser energy as compared to the energy required for the production of the platinum 2 positive ions. So in the case of the nickel, this energy is lesser as compared to the platinum. So automatically nickel 2 positive compounds will formed easily, and therefore these compounds are thermodynamically more stable than the platinum 4 compounds. But if we want to convert nickel to nickel 4 positive ions, then it requires this much amount of energy, that is the 11290 kilojoule per mole. But in case of platinum, if we want to convert it into the platinum 4 positive ions, then it requires this much amount of energy, that is the 9360 kilojoule per mole. So it's clear from this, that is the formation of this platinum 4 positive ions requires lesser energy as compared to that required for the formation of nickel 4 positive. So automatically platinum 4 positive ions will be easily formed, and so these compounds are more stable than the nickel 4 positive compounds. And this is supported by the fact that this particular complex ion is known, whereas the corresponding ion for the nickel is not known. Why? Because to convert the nickel into the nickel 4 positive ions, it requires a huge amount of the energy. Clear? So from this, it is clear that in the case of the D block elements, the higher oxidation states are more stable for the heavier members like platinum in a group. So next property is the oxidation state. All the transition elements aside from the first and the last individual from the series display various oxidation states. कि वो क्या करते हैं, अलग-अलग oxidation states को show करते हैं. They indicate variable valency in their compounds. And some fundamental oxidation conditions of the first, second and third transition series elements are given in the tables as the oxidation state for the first series, that is the 3D series. In the case of the scandium, the oxidation state is +2 and +3. Similarly, in the case of titanium, it's +2, +3, +4 and goes on up to the manganese. It can show a number of the oxidation state, that it can show the +7 oxidation state also. Similarly, all the other members can show a number of the different oxidation states. Similarly, the members of the another series, that is the 4D series, also show a number of the variable oxidation states. Like ruthenium, they can show the oxidation state of the +8 also. So next is that is the 5D series. Again, in this case, the members can show different oxidation states. So they show variable oxidation states unlike S and the P block elements, and their oxidation states changes in the units of the 1. For example, Fe2 positive and Fe3 positive, copper 1 positive and copper 2 positive. Why they are showing the variable oxidation states? Since the energy difference between the S and the D orbital are very small, so in this case both the electrons can involve in the ionic and the covalent bond formation. So that's why they can show multiple oxidation स्टेट्स। क्यों? क्योंकि इसमें क्या होगा कि आपकी ns ऑर्बिटल भी पार्टिसिपेट कर सकते हैं और n-1 d ऑर्बिटल्स वाले जो इलेक्ट्रॉन्स होंगे वो भी पार्टिसिपेट कर सकते हैं। तो उसकी वजह से क्या होगा, these elements can show a number of the oxidation state. Each transition element can hence exhibit a minimum oxidation state which is corresponding to the number of the s electrons, and maximum oxidation state that is equal to the total number of electrons available in both s and the d orbitals, and in between oxidation states also become possible. Like scandium can have an oxidation number of the +2 if both s electrons are used for the bonding, but it can also show the +3 oxidation state when 2s and 1d electrons are involved in the bonding. Similarly, all the other elements show variable oxidation states which depends upon the number of electrons available for bonding in their s and the d subshells. ये किस पे डिपेंड करेगा कि आपका एलिमेंट कितनी ऑक्सीडेशन स्टेट शो कर सकता है, उसके नंबर ऑफ इलेक्ट्रॉन्स पे कि s ऑर्बिटल में कितने इलेक्ट्रॉन्स अवेलेबल हैं और d पे कितने। जो कोई भी एलिमेंट की मिनिमम ऑक्सीडेशन स्टेट होगी वो किसके इक्विवेलेंट होगी कि उसके s ऑर्बिटल में कितने इलेक्ट्रॉन्स प्रेजेंट है, और मैक्सिमम की मैक्सिमम ऑक्सीडेशन स्टेट किसके इक्विवेलेंट होगी कि total number of electrons which are available in both s and the d orbitals. So next is the some important features of oxidation state of transition metals are, जो most basic oxidation state होगी 3D series की वो क्या है बेटा, +2 with the exception of the scandium because of the loss of 2 ns electrons, which demonstrate that d orbitals become more stable than s orbital after the scandium. And ionic bond are generally formed in only in the +2 or the +3 oxidation state, whereas the covalent bonds are formed in the higher oxidation state. For example, in case of the permanganate ion, the manganese can show the +7 oxidation state. So in this case, all the bonds which are formed between the manganese and the oxygen is covalent one. कि जो आयनिक बॉन्ड है वो लोअर ऑक्सीडेशन स्टेट में बनेगा, whereas the covalent bond is formed in the higher oxidation states. Next is the oxidation state generally increases with increase in the nuclear number of the element that achieves greatest in the center and after that begins diminishing as appeared in the table, कि जो हम already table में देख चुके हैं. For example, iron shows the normal oxidation state of +2 and +3, while ruthenium and osmium in a similar group can form compounds in the oxidation state +4, +6 and also in the +8 oxidation state. कि जैसे जैसे न्यूक्लियर नंबर बढ़ता जाएगा कि एटॉमिक नंबर बढ़ता जाएगा वैसे वैसे क्या होगा, जो ऑक्सीडेशन स्टेट है वो भी क्या होती जाएगी बेटा, इंक्रीज होती जाएगी, विच इज ग्रेटेस्ट इन द सेंटर. सेंटर पे वो मैक्सिमम होगी जैसे इन केस ऑफ रुथीनियम और ऑस्मियम, एंड आफ्टर दैट इट बिगिंस डिमिनिशिंग कि वो क्या होती जाएगी, डिक्रीज होती जाएगी. So next is the higher oxidation states are more stable in case of the heavier elements, like in molybdenum, that is the +6, tungsten +6 are more stable than the chromium 6. So next is the relative stability of elements which exist in more than one oxidation state can be known from the standard electrode potential value. कि अगर हमारे पास कोई भी एक एलिमेंट एक से ज्यादा ऑक्सीडेशन स्टेट में एग्जिस्ट कर सकता है तो हम उसकी स्टेबिलिटी किसके बिहाफ पे बता सकते हैं, स्टैंडर्ड इलेक्ट्रोड पोटेंशियल के बिहाफ पे. लोअर द वैल्यू ऑफ स्टैंडर्ड इलेक्ट्रोड पोटेंशियल, मोर स्टेबल इज द ऑक्सीडेशन स्टेट ऑफ मेटल इन द एक्वस स्टेट. जितनी ज्यादा बेटा इलेक्ट्रोड पोटेंशियल की वैल्यू कम होगी उतना ही ज्यादा हमारी ऑक्सीडेशन स्टेट की होगी ज्यादा स्टेबल होगी. क्लियर? सो लाइक titanium 4 positive is more stable than the titanium 3 positive. Why is it so? Because in case of titanium 4 positive, the electronic configuration is 3d 0, that is the empty d orbital, whereas in case of titanium 3 positive, it's a 3d 1. So empty, this is a more stable as compared to this. So that's why titanium 4 positive is more stable than the titanium 3 positive. Similarly, manganese 2 positive is more stable than the manganese 3 positive. Why? In case of the manganese 2 positive, electronic configuration is D5, exactly half-filled configuration. That is the more stable. So that's why it is more stable than the manganese 3 positive, which is having the 3d4 electronic configuration. So next property beta, that is the formation of the colored compounds. Most of the d block metal compounds are colored whether they are in the solid state or in the liquid state. As in case of transition metal ions, under the influence of ligands, the degeneracy of the 5d orbitals is lost and they separate into two distinct energy levels. बेटा degeneracy क्या होती है कि 5d d orbitals are generally degenerate. That is all the orbitals are having the same energy. But when the ligand approach to the transition metal ions, कि जब भी वो ligand metal ion को approach करता है जिसके साथ वो मिलके कोई भी compound या कोई complex बना रहे हैं, तो उस वक्त क्या होगा कि जो degeneracy होगी that is lost, कि जो आपके 5d orbitals है उनकी energy क्या equal नहीं रहेगी, वो क्या हो जाएंगे, break हो जाएंगे to different energy levels. One is the Eg set, another is the T2G set. Eg set is having two orbitals, that is the dx2 y2 and dzk orbital, and T2G is dxy, dxz and dyz orbital. This state is the unstable in nature. क्यों? क्योंकि हायर एनर्जी है तो अनस्टेबल होगा. जो इलेक्ट्रॉन यहाँ पे पहुंचेगा वो क्या करेगा, वो अनस्टेबल फॉर्म में आ जाएगा. तो वो क्या करेगा, वापस किस फॉर्म में जाना चाहेगा, स्टेबल फॉर्म में. दैट इज टू द T2G set. So it comes back to the lower energy level and emits the extra energy again in the form of the radiation. So that's why the compound is visible like a colored one. So the color observed corresponds to the complementary color of the light absorbed. कि जो कलर हमें दिखाई देगा वो कौन सा कलर होगा, जो किसका कॉम्प्लीमेंट्री कलर होगा, जो लाइट हमारा सैंपल एब्जॉर्ब कर रहा है. एंड द फ्रीक्वेंसी ऑफ द लाइट एब्जॉर्ब्ड इज डिटरमिन्ड बाय द नेचर ऑफ द लिगेंड. कि कौन सी फ्रीक्वेंसी की लाइट हमारा सैंपल एब्जॉर्ब करेगा वो किस पे डिपेंड करेगा, नेचर ऑफ द लिगेंड पे. क्लियर? So next is that is there are some exceptional case, that is the zinc 2 positive, cadmium 2 positive. In these case all the d orbitals are the fully filled. But in case of the titanium 4 positive, all the d orbitals are the vacant. So in these cases there is a no dd transition possible. क्यों? एक तो already filled है तो इलेक्ट्रॉन एनर्जी एब्जॉर्ब करके हायर एनर्जी लेवल में पॉसिबिलिटी नहीं है जाने की, वो ऑलरेडी फिल्ड है, कंप्लीटली फिल्ड है. ठीक है जी. और टाइटेनियम 4 के केस में दोनों सेट्स में कोई भी इलेक्ट्रॉन नहीं है, वेकेंट है. सो नो dd transition is possible in that case. So therefore they do not absorb radiations and that's why they are the colorless in nature. Clear? Except these all the other compounds, yeah, you can say all the other transition metal ions shows the color. So next property, that is the formation of the complex compounds. Metal ions bind a number of the anions like cyanide ion or the neutral molecules, that is the ammonia, giving a number of the complex, that is these one. Why they are forming a number of the complex compound? It is due to the comparatively smaller size of their central metal ions and their higher ionic charges and the availability of the d orbitals for the bond formation. क्यों ये इतने ज्यादा compounds बनाते हैं? एक तो जो transition metal ion का size है वो क्या है बेटा, small. Second, due to their high ionic charge, that is they can show a number of the variable oxidation state. They can show the oxidation state up to the +8 also. So third is the d orbital is available in these elements for the bond formation. So next property is that is the formation of the interstitial compounds. Transition metals form a number of the interstitial compounds, that is when the small atoms like hydrogen, carbon or nitrogen are trapped inside the empty spaces in the crystal lattices of the metals, then they form the interstitial compounds. These empty spaces are known as the interstitial spaces. Clear? इन empty spaces में बेटा सिर्फ वही वाले atoms trap होंगे जिनका size इनके empty space के size के साथ क्या होगा, match करता होगा. वो easily trap हो जाएंगे. ठीक है? Clear? And they form a new compound which is known as the interstitial compounds. And these interstitial compounds are generally non-stoichiometric. Non-stoichiometric means कि in these cases the ratio between the two atoms is not the same one, it is the different one. Like in this case vanadium hydride. Clear? In this case vanadium is 1 and the hydrogen is 0.56. So and these are the generally non-stoichiometric one, and bonds formed in them are neither covalent nor the ionic one. ना तो वो covalent होंगे ना ही वो क्या होंगे बेटा ionic bonds होंगे. Clear? So next is the important characteristics of the interstitial compounds. The interstitial compounds have high melting points, even then higher than those of the pure metals, and they are the very hard. Some borides approach diamond in the hardness. कि कुछ borides compounds ऐसे होंगे जिनकी जो hardness होगी किसके साथ comparable होगी diamond के साथ, and they retain their metallic conductivity. That is, they are the good conductors of electricity. Clear? And next is they are the chemically inert, कि वो किसी भी चीज के साथ react नहीं करेंगे. They are the inert one. So our next property, that is the alloy formation. Alloys are homogeneous, मतलब same, solid solutions of two or more metals obtained by melting the components of two or more metals and cooling the melt. Clear? कि दो से ज्यादा metals को हम क्या करेंगे, उनके components को melt कर लेंगे, फिर उस melt को हम क्या करेंगे, cool करेंगे. That will become the homogeneous mixture of the two or more metals, which is known as the alloys. And alloys are generally formed by only those metals whose atomic radii is not differ by more than 15%, कि जिनका जो atomic radii है वो almost क्या होना चाहिए, same होना चाहिए, जिसमें 15% से ज़्यादा difference नहीं होना चाहिए. Clear? And in case of the transition elements, they form a number of the alloys. Why? Because of their similar radii, they can easily form the alloys. And the alloys formed by them are the hard and often having high melting points. Clear? And alloys of the transition metals with the non-transition metals such as the brass, that is, and the bronze. That is, brass is the alloy of the copper and the zinc, whereas the bronze is an alloy of the elements copper and the tin. So next property, that is the catalytic properties. Catalysts are important for the industrial bulk production of many chemicals. In today's life, in most of the production of the chemicals, a number of the catalysts are used. Actually, catalyst is a substance which generally increases the speed of the reaction, but itself is not used in the reaction. जो खुद reaction में use नहीं होता, सिर्फ क्या करेगा, उसकी speed को increase करेगा by lowering its activation energy. Clear? And many D block elements as metals are in their ionic form are being used as a catalyst in many chemical and biological reactions. कि जो D block elements हैं, most of the D block elements are used as a catalyst in a number of the chemical processes or in the biological reactions. For example, iron used in the Haber's process to manufacture the ammonia, vanadium pentoxide in the manufacture of the sulfuric acid. Similarly, palladium chloride in the conversion of ethylene to the acetaldehyde. These are the few important commercial catalysts which are used in a number of the processes, and these are generally from the D block elements. Most transition elements act as good catalysts. Most of the transition elements है बेटा वो क्या करते हैं, good catalyst की तरह काम करते हैं. क्यों? Because of the reason that is the presence of the vacant d orbital. कि एक तो उनके पास जो vacant d orbital present है. Second is their tendency to show a variable oxidation states. They can show a number of the oxidation states. And third is their tendency to form the reaction intermediates with the reactants. Clear? एक तो उनके पास vacant d orbital है, variable oxidation state show कर सकते हैं, एक वो number of the reaction intermediates form कर सकते हैं with the reactants. And they take the reaction through a path of the low activation energy by providing a large surface area for the absorption and allowing sufficient time to react. कि वो किस तरह एक नया पाथ प्रोवाइड करते हैं लो एक्टिवेशन एनर्जी का, कि जिससे जो रिएक्शन स्पीड है वो इंक्रीज हो सके. वन इज एक तो वो सरफेस एरिया ज्यादा प्रोवाइड करते हैं फॉर द एब्जॉर्प्शन के लिए एंड अलाउइंग सफिशिएंट टाइम टू द रिएक्ट. सेकंड इज दे मे इंटरैक्ट विद द रिएक्टेंट्स through their empty d orbitals. Clear? Third is may actively interact by the redox reaction through their multiple oxidation states. क्योंकि वो variable oxidation state show कर सकते हैं, तो उसकी वजह से वो क्या करेंगे, they may also interact with the reactant by the redox reaction, or they may also interact with the reactants by their empty orbitals, and third is they can also provide a large surface area for the absorption of the reactant and providing them the sufficient time to react with each other. So by this way they increase the speed of the reaction by providing a path of the low activation energy. Clear? So our next property, that is the magnetic properties, that is the substances which contain species, that is atoms, ions, molecules with unpaired electrons in their orbitals, they are known as the paramagnetic substances. Whereas which do not contain any unpaired electron and they are repelled by the magnetic field, they are known as the diamagnetic substances. Whereas the paramagnetic substances are attracted by the magnetic field as they are having the unpaired electrons. And we have seen that in the earlier cases, that is the transition metals usually contains unpaired electrons. So they are the paramagnetic in nature. And their paramagnetic behavior increases with increase in the number of the unpaired electrons. जैसे जैसे unpaired electrons का number बढ़ता जाएगा, जो paramagnetic behavior है वो क्या होता जाएगा बेटा, बढ़ता जाएगा. And this paramagnetism is expressed in terms of the magnetic moment which is related to the unpaired electrons. And the magnetic moments, it is calculated from the spin only formula कि जो magnetic moment सिर्फ spin की वजह से होगा, electronic spin की वजह से, it is calculated from the spin only formula, that is the mu, which is the symbol of the magnetic moment, equals to a square root of n bracket n plus 2 and bm, where n is the number of the unpaired electron, bm is the Bohr magneton, that is the unit of the magnetic moment, and 1 bm is equals to the 9.27 into 10 raised to power minus 21 ergs per Gauss. Clear? कि जैसे जैसे तो इस फॉर्मूला से भी हमें क्लियर हो रहा है कि जैसे जैसे नंबर ऑफ अनपेड इलेक्ट्रॉन्स बढ़ता जाएगा, n का नंबर बढ़ता जाएगा, हमारा मैग्नेटिक मोमेंट की वैल्यू क्या होती जाएगी, बढ़ती जाएगी. और जितनी ज्यादा हमारा मैग्नेटिक मोमेंट आएगा उतना ही हमारा सब्सटेंस पैरामैग्नेटिक कैरेक्टर क्या करेगा, शो करेगा. क्लियर? So in case of the single unpaired electron, that is having the magnetic moment of 1.73 bm. So clear? So with this our properties are complete. Thank you.